My name is Henriko Rayyan with name F1D02410050. And in this video, I will present my final project, which implement numerical data processing using a hybrid approach, which combining CUDA and PySpark. So the main goal of this project is to perform computational operation on array of 1000 random numbers and directly comparing the execution time and observing how both technologies handle parallelism. So let's break down the parallel concept first. So the first point of parallelism is in CUDA. CUDA utilizes the GPU architecture, which consists of 1000 tiny cores to perform computation simultaneously. So in this C code, I define the grid and blocks. It was here. So I configured each block to have 256 threads. When mathematical operations like squaring or normalization are executed, they are not processed one by one sequentially. Instead, each element of the data array is processed by a different thread at the exact time. You can see this is in the EDX variable, which calculate the global thread position. The single instruction multiple thread approach is what makes CUDA incredibly fast for large-scale numerical processing. So the next is CUDA simulator.py. And here, as a fallback mechanism, I also built a simulator using NumPy. If this program is run on a machine without the NVIDIA GPU hardware, it will automatically simulate this grid and block distribution through software using a standard CPU. This ensures the logic of the CUDA architecture can still be demonstrated smoothly without throwing any hardware-related error. And I have PySpark ops.py. So there are the function I will give to the main.py. The first one. So the second point of parallelism is in PySpark. Unlike CUDA, which focuses on GPU threads, PySpark distributes the workload across GPU cores using resilient distributed dataset or RDD. So here I am implemented four specific PySpark processing method for comparison. The first one is Spark query, and which convert the data into a data frame and uses SQL syntax to find the maximum, minimum, and average values. The second one is the map. This is to perform parallel data transformation. So in this case, querying the element. The third one is reduce. Reduce is used for aggregate the data element to find the total sum. And the last one is filter, to parallelly filter the data to find values above the mean. So all this process run to concurrently in the background using worker nodes allocated in the local memory. And in the result of this project, so the execution result, after running the program, I can validate that the reduced sum calculation from both CUDA and PySpark produce identical numbers. This means the mathematical logic for both is perfectly valid. However, in the execution time comparison section, there is a very significant difference. The total execution time for CUDA is much faster than any of the PySpark method. So why this happens? PySpark is specifically designed for big data ecosystem dealing with terabytes of data across multi-server cluster. For processing just 1000 simple data element, PySpark actually takes longer due to overhead, meaning the preparation time required to start the Spark session communicate between nodes and allocate workers. Conversely, CUDA directly execute the numerical array operation at the hardware level, making it absolute winner for this specific data size. So, in this conclusion, integrating PySpark and CUDA demonstrate that choosing the right technology heavily depends on your data architecture. CUDA excels in an intensive mathematical computation, while PySpark is much better suited for distributing massive data pipelines. And that's all my presentation of my final project. Thank you for watching.